This video is going to start us out in our final chapter, Chapter 8, where we will be talking about circles. So some of the information in this video should be old information. There will be quite a bit new information. I'm sorry it's kind of a long one because there's a lot of stuff to cover and to go over. So just kind of sit tight, bear with us, and we'll see what we come up with. All right, in the first one, we're going to talk about a few segments that occur within circles. So two of these are things you should already know, but I did use a terminology image here. I don't know if you know, but you symbolize the word circle with what looks like a little circle with a center, and you name a circle by the point at its center. So this would be circle C. Now remember, by definition, a circle is a set of all the points that are equidistant or the same distance from that center. And in this particular image, there are two lines that you should see. One of them is all the way over here from A through the center and over to B, and that one should be something you're familiar with. So AB, the entire segment, is a diameter. Hopefully you're comfortable with that word. All the way across the circle through the center. And CD in this diagram, so from the center out to point D, so from the center to the circle, is a radius. And you've used those in the past when you have found circumference, area, those types of things. So those two I would expect to be familiar vocab terms for you. Now let's look at three other vocab terms that are segments within our circle, probably ones you are not familiar with. So we're going to start out with JL. You will notice that JL is a line. It doesn't stop at J and L. It doesn't have endpoints. It has arrows at each end. It just keeps going all the way through the circle. When a line cuts through your circle like that, it has to have a line symbol on it, and that is what we call a secant. Secant. Cuts through the circle and keeps going. Now FG also cuts through the circle, but the difference between JL and FG is JL keeps going. FG has endpoints, so an endpoint on the circle and another endpoint on the circle. So it's just through the circle, but it has a start and a stop. And that is called a chord. So the reality is, up here when we had AB, which is a diameter, is also a chord. It's just a more specific type of chord, but it has endpoints on our circle. And then we have this last one out here, line N, and we know most lines are named by a cursive lowercase letter. Why, I don't know, but that's the way it is. So we usually have like a lowercase n, L, T, M, whatever the letter might be, but it's usually going to be lowercase cursive. And it happens to touch the circle right here at this one point, that's H. And so this line that touches the circle one time, you will notice that line never goes inside of the circle. It stays on the outside. That is called a tangent. Now you've heard that word before when we did sine, cosine, and tangent, but this is a different type of tangent. This one's tangent to a circle. And that point H, the one spot where it touches the circle, that point is called a point of tangency. That just names for us the point where it touches the circle. So let's take a look at another diagram, and we're going to now this time have the vocab word, and we're going to name what we see in the figure. So a radius. Remember, a radius is from the middle to the edge of the circle. So coming out of the middle, we could name PT, PS, or PR. Any of those are considered a radius. I'm going to just probably do PS. And it is a segment, so it'll have a line over top with no arrows. A diameter has to go across the circle and through the center. So through the center, the line I'm seeing is R through P and all the way to T. So from R and ending at T. So R, T, and again, it will have a line over top because it does not keep going. It has endpoints. We will not use any arrows. A chord. So RT is a chord, but it's a special chord. There's another one. Endpoint R to endpoint S. So endpoint to endpoint would be another chord, RS, with a segment. Now the secant, remember, cuts through the circle but keeps going. So when we look at our diagram, through the circle but keeps going, we're looking for arrows. So this one has arrows, but it doesn't go through the circle. This one has arrows and does go through the circle. So QT, and we would need to name that as a line, so it's going to have arrows over top. And then our tangent, here's the point of tangency. The only line that does not go through or inside of the circle is this line right here. It's named up here with a lowercase l, so the tangent will be line L. All right, hopefully those vocab terms make sense to you. Now the tangent, the one that never goes inside of the circle, it has several properties, like several. So the first one we're going to talk about is this one. The tangent and a radius to the point of tangency are perpendicular. So in this diagram, here's my tangent, line T, and here's a radius right here from A to the point of tangency. When there's a radius drawn in there and we have a tangent, this will be perpendicular, which remember means a 90-degree angle. So we're going to form 90-degree angles there. The next property is two tangents intersect at an external point that is equidistant from the points of tangency. Okay, now that was a big mouthful. Here's its diagram. Two tangents. So this is a tangent, AC. If I were to keep it going like that, it would not go through the circle, and if I were to keep this one going, it would not go through the circle. So here's my two tangents, AC and BC. If they meet at an external point, that means outside of the circle, then they are equidistant from the point of tangency. So from C to A and from C to B, those two lengths are going to be the same. So if I told you this one is 12, then this one would have to be 12. Okay, those two lengths have to be the same. Okay, so let's kind of put that together with something from the last chapter. So here I have points of tangency out here. If I were to keep those lines going, they would not go inside of the circle. So I have points of tangency. Do you see the shape I see? If these are the same length, because that's what the theorem tells us, guess what? A radius from the center to a point on the circle and from the center to a point on the circle, doesn't matter where you draw the radius, it has to be the same. Do you see the kite? I'm seeing a kite. And we know in a kite that we are going to have a quadrilateral. All the angles are going to add up to 360. We also know that these opposite corners are going to be congruent, and we happen to know what they are because points of tangency and a radius are perpendicular. So we know we have 90-degree angles happening in each corner. So I can find the value of x by recognizing that this is a quadrilateral, and quadrilaterals always add up to 360. So 90 plus 130 plus 90 plus x, all together, those have to add up to equal 360. So we can add these together. Oh, let's see, those two are going to make 180. Then 180 and 130 would be 310. So 310 plus x will equal 360. We'll subtract our 310 on each side, and we get x to be 50 degrees. So the angle down here at this little corner of the external point would be 50 degrees. All right, some that are a little bit tougher. Is line AB tangent to circle C? Well, if it's tangent, then this would be a 90-degree angle. So we're really asking, is that a 90-degree angle? Well, if it's going to be a 90-degree angle, then the Pythagorean theorem would hold true. And this distance way over here would be our hypotenuse, and these two would be our legs. So our Pythagorean theorem would tell us that leg squared plus leg squared is equal to hypotenuse squared. So this is what we're asking. Are those equal? If they're equal, then it's a 90-degree angle. And if that's a 90-degree angle, then AB is tangent. So let's calculate. Let's see here. We have 81, 121, I don't know, 14.9 squared off the top of my head. So I'm going to grab my daughter's calculator. 14.9 squared is 222.01. And then we're going to add those together. I don't want to get that wrong, so I'm going to just, since the calculator's hanging out here, I've got 202 equaling 222 0.01. So if those are not equal, then this is not a right triangle, because the Pythagorean theorem, that has to be true. So if these are not equal, then this cannot be a right triangle. And if that's not a right angle, then there's no way that line AB is tangent. Remember, it has to hold to be a 90-degree angle. I started to write a funny letter. I don't know. I was trying to write is not tangent to circle C. All right, let's take a look at another example similar to that. So here we are asked if AB is tangent to circle C. So if this is a tangent, then at the point of tangency would be a 90-degree angle. So we're asking, is that a 90-degree angle? If it's a 90-degree angle, then the Pythagorean theorem has to hold true. So across from the 90-degree angle would be this side. That would be our hypotenuse. So our legs would be 5 and 7. So 5 squared plus 7 squared is equal to 8.6 squared. And that's what we want to know. Are they equal? So 5 squared is 25. 7 squared is 49. I don't know 8.6 squared, so we're going to grab that calculator again. And we get 73.96. Then we're going to add 25 and 49, and we get 74, equaling 73.96. Now, I'd be a lot happier if those were actually the exact same number. However, I understand that if I had to round here to get 8.6, then this would probably be a rounded answer, which is pretty much 74. So I'm going to go with the fact that, yes, AB is tangent to circle C. Again, I'd be happier if that said 74 equals 74, but we go with what we've got. So AB is tangent to circle C because we proved the Pythagorean theorem to hold true in that diagram. Now the really tricky ones. Find the radius of circle P. ST is tangent to circle P. So here we have a diagram. We know this is a right triangle because we're told it is tangent. So we're going to be looking at the Pythagorean theorem once again. Now across from the 90-degree angle is our hypotenuse, so this length over here. But you will notice the hypotenuse is not labeled with one value. There's an R that goes from the center to the circle, but then there's another 1 right here. So the length of the hypotenuse would be both of those together. It would be R plus 1, whatever R happens to be, which is what we're going to calculate. The legs are R and 3. So we have R squared plus 3 squared, those are the legs, equals the hypotenuse, R plus 1, squared. Now R squared I can't do anything with. 3 squared is 9. Now over here, this takes us back to chapter 2, when we had a binomial squared. So we learned when you have a binomial squared, you have to write it twice and multiply that out. So R times R is R squared. R times 1 is R. 1 times R is R, and 1 times 1 is 1. Collecting our like terms in the middle, we get R squared plus 2R plus 1. Now if you remember square double square, this still works and you can use that shortcut. Okay, R squared plus 2R plus 1. Now we'll need to collect like terms. So I see my highest power is an R squared, so I'm going to take that one. I want to do its opposite. I like things to be on the left-hand side whenever possible. But R squared minus R squared, that cancels out, so I have 9 equals, and R squared minus R squared cancels out, so I just have 2R plus 1. Now, those R squareds nicely canceled out. We're down to just R's, so we're going to subtract our 1 from each side and divide by our 2, and we find out that our radius for that circle equals 4. So this is 4. And this distance would be 4 plus 1, so this hypotenuse would have a length of 5. Let's do that one more time just to make sure you followed through that process. Remember, ST is tangent, so that means this is a 90-degree angle. So we are looking at across from the 90-degree angle is our hypotenuse. So the hypotenuse would not just be this length of R, but R and this length right here of 5 together. So we would want to express that as R plus 5. Using the Pythagorean theorem, we know then our legs to be r and 10. So r squared plus 10 squared will equal the hypotenuse, which we know to be r plus 5, squared. R squared is just going to stay r squared. 10 squared will be 100. And then r plus 5 squared, we either need to do side work or remember square double square. So r plus 5 and r plus 5. Multiplying r and r, we get r squared. R and 5, 5r. 5 and r, 5r. And 5 and 5, 25. Collecting our like terms in the middle, we get r squared plus 10r plus 25, or square r, multiply these two and get 5r and double it to get 10r, and 5 squared is 25. You get the same answer whether we used square double square or if we did the side work and multiplied all that out. Now I want to get my like terms together, so I'm going to subtract the r squared. These cancel out and we have 100 equals. These cancel out, so we now have 10r plus 25. So we'll subtract our 25 over on this side. That gives me 75 equals 10r. Then we'll divide both sides by 10, and we get 7/2 as the value of the radius. So our radius in this case is 7.5. That 7.5 would go here and here. So the length of this side would be 7.5 plus the 5, so 12.5 for the length of the hypotenuse. The last thing that I want to cover for this lesson is common tangents. So remember, a tangent touches the circle one time and it stays on the outside of the circle. So common tangents mean you have more than one circle and you're looking for lines that touch each of the circles one time. That would be a common tangent. So when we have overlapping circles, if I were to draw a line, I'll call it the top, I don't really have a better term for that, but if I were to draw a line up here across along the top of those two circles, I gotta get where my straight edge will work. I can draw a line that's going to go across and touches the tops of each of those circles, and then I should be able to do the same thing down here along the bottom of the two circles. These are called external common tangents because they stay outside of the two circles. They don't come in between them or anything like that. So this one has 2 common tangents. When the circles are inside of one another, but they share a point out here, if I go with one line that is tangent to that single point, then that line would be tangent to both of the circles at that one point. So they have one line of tangency. If my circles are side by side and touching in one point, then I have the 2 that I had up here because I can go across the tops and bottoms of the 2 side by side circles. Let me do that one. There I have one. And then I can do the same thing along the bottoms, so to speak. So I have those 2. But I actually have another point or another line of tangency because I could go right through the middle if I go right through the point that they share. So there's 1, 2, 3 common tangents for this pair of circles. And then if I have circles that are next to each other but not touching, this is when I have the most. So I could still go along the top and bottom of the 2 circles, just like we did in the very first one and then in the last one. I can go the top and bottom. Oops, didn't line my straight edge up very well on that one. But then I actually have 2 more that I can draw in because I can go through the center, so to speak, in like an X shape, and I can go this way to touch this circle right here and this circle right here, or I can go the other direction in order to touch this circle here and this circle here. So here we have the top the bottom, and the two that make the X, so these two have 4 common tangents. And the last thing that could happen is we could have concentric circles, which means that one is directly inside of the other. They would like have the exact same center, they would just be different distances from that center. And in this case there are no common tangents, because if I want to draw a line that touches that inside circle, then I have to go into or through the outer large circle. I can't draw anything that would touch the inside circle and only touch the outside circle once. All right, I know that was a long one, so thanks for bearing with me, and if you have any questions, as always, don't hesitate to give me a call.